Greetings, Chem 2 students. Mr. Keister here with you again today. Today is the video for Monday, September 21st, 2020, which is our scheduled 22nd day, I believe. Yes, our 22nd day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order of those lessons will remain the same regardless. I'm dressed a little casual here today. I'm actually recording this video on a Saturday, so now you can see what I look like at home. Anyway, today is a scheduled e-learning today, so all of you will be home today doing your work there. And again, on an scheduled e-learning day or any day that you are absent, you are to follow the exact same routine as you would if we were all here in class. All right, and that of course starts with our daily schedule and the do now. So let's take a look at that. So today we're going to go over a little more discussion in Unit 2.2 on nuclear discoveries and nuclear chemistry. I actually handed this out Friday in class. Lab 2.1, the half-life of Pentium. All right, we're going to, after I go through a brief discussion here on the board, we're going to head to the back and do that. Your homework for today was to complete the nuclear equations assignment on Friday. That is due now. So whatever your class schedule is, you should be turning that in at the beginning of that class schedule time. You will submit it to me en masse through Canvas. All right, no email attachments today. This is since it's not an individual absence, where we're all absent. So you will submit it to me through Canvas. You should know how to do that. So just click on the assignments. It'll show up, or the assignments tab on my homepage, and it will come up, and you submit it from there. All right, so make sure you do that. Of course, the answer key is posted here on the board, which doesn't do you much good today, but it is also posted on the answer keys tab in Canvas. So today we're going to first go over nuclear transmutations and then begin our discussion of radioactive decay and half-life. After that, we'll head back to the lab area and do lab 2.1, the half-life of Pentium. This is a lab that you guys did in regular chemistry. Of course, you guys are in Chem 2. So this is a lab you did in regular chemistry. But regardless of that, it is such a good lab and such a good demo of half-life that we got to do it again. All right, we got to. It's just, it's a good one, and it explains half-life extremely well in regards to what it is and how it's graphed. And so this is an exercise well worth doing again. Your completed lab report is to be turned in tomorrow at the beginning of class when you return to school. All right. There will be an answer key posted with sample data that I did today on it, so you can check to see that you're doing that correctly. Again, that will be here on the board as of 7 a.m. tomorrow morning. It will also be posted in Canvas at the same time on the answer keys page, so you could check it there as well. So, having said all that, let's get to today's lesson. And we're going to talk about Ernest Rutherford yet again. This was one busy dude, all right? Like I said before, he isn't called the father of nuclear science for nothing, because he did so much in regards to not only atomic theory, but his work with radioactivity. And now here he is again with yet another major discovery. Okay, so let's take a look here and talk about him again. So in 1919, Rutherford observed the first nuclear transmutation, which is the conversion of the nucleus of one element to that of another by particle bombardment. That particle could be one of our nuclear particles, radioactive nuclear particles, that is, alpha, beta, or gamma, or it could also be a neutron. And in fact, I want to kind of step aside just for a second and talk about a nuclear transmutation involving the bombardment of a radioactive isotope by a neutron, because this is exactly what we do in a nuclear reactor, all right, in producing electricity using nuclear energy to do that. It is also the same setup, the same procedure that also would set off a nuclear bomb, all right, where a heavy radioactive isotope such as uranium or plutonium is bombarded with a neutron, which starts the whole thing going. The only difference is in a bomb, all that energy is released at one time. In a reactor, it is controlled, and we'll talk about that a little later. All right. So let's take a look here. We've got some room down here on the notes. We're going to do a little writing in here. This is called neutron-induced fission. All right. Not fission that you do in the lake up by my house, but fission, which is the splitting of a radioactive isotope by particle bombardment. Of course, these are done at high speed. They force them in there and they split the larger nucleus apart. And in doing so, we get some products as well as a whole bunch of heat energy, all right, which in a reactor we use to produce electricity. In a bomb, of course, we use to cause major destruction. Thankfully, we haven't done any of those in a very long time, and I hope we never do. But anyway, this is what's done primarily in a nuclear reactor. Let me first say that a nuclear reactor is an extremely efficient method of producing electricity. All right, you can burn tons and tons of coal to produce the same amount of heat energy that a very small amount of nuclear material will produce. And it doesn't spit out all the particulate matter and polluted gases into the atmosphere either that burning coal does as well. So nuclear reactors, of course, you've got some things to deal with in regards to safety issues, but we have been managing that for years here with literally hardly any issues at all. And so it is an extremely efficient way to produce electricity. So neutron induced, what does that mean? Well, it means you need a neutron to start the thing rolling. So let's start with uranium-235, which is a source of fuel that we primarily use in a lot of reactors. And we've got to add a neutron to that. That's what neutron-induced means, all right? So we shoot a neutron at an isotope of uranium-235, and it splits it, all right? And here's what happens. First thing it does is it combines with uranium-235 and gives us uranium-236, all right? Just following the conservation of mass like we did with our nuclear equations, all right? 235 and 1 is 236. Atomic number stays the same. Uranium-236 is highly unstable, and it immediately then splits apart into barium-144 and krypton-89 and, well, let's look. Let's see if we figure that out. 56 and 36 is equal to 92. All right, so this is a 0. All right, 144 and 89 is 233. We start with 236. That leaves us 3. We talked about this Friday. There is no such thing as 3-0, but what do we know about that can get us those numbers? And if you remember, well, a neutron is 1-0, and that would produce then 3 neutrons, all right? Plus a lot of heat energy. And by a lot, I mean a tremendous amount, all right? Now, here's what happens. These 3 neutrons that are produced are then reacted with additional isotopes of uranium-235, and the reaction just keeps going and going. It's self-sustaining, all right? This is called a chain reaction because once it starts, until you run out of either uranium-235, well, you'd have to run out of that because the reaction's going to keep producing neutrons. Until you run out of uranium-235, this reaction is just going to keep going and going and going, all right? That's why we call it a chain reaction. So these neutrons react with additional uranium-235 isotope. Again, in a reactor, we can control the speed of this reaction and thus the amount of heat given off at any given time. In a nuclear bomb, the whole idea is to have it all go off at one time, okay? So this is one type of nuclear transmutation where you start with uranium-235 and you end up with completely different elements, all right? Completely different elements. Okay, let's go on to the next page. I wanted to tell you that first because it plays such an important role in energy production. Like I said, we got to deal with the radioactive decay that's going on. We'll talk about that tomorrow. And so there are some issues safety issues we have to be aware of. But like I said, we've been managing that for years. Literally, well, let's see, it started in the 50s. 70 years. We've had one minor accident here in the United States. We'll talk about that tomorrow. There was not a major release of radiation. Of course, we've had a big one over in Russia and the Ukraine back in 1986. If you've read or heard or seen the movie about the Chernobyl disaster, So anyway, we'll mention that a little bit tomorrow. So Rutherford found that by bombarding, here's how he discovered a nuclear transmutation. He found that by bombarding the isotope of nitrogen-14 with alpha particles, he could produce a yet undiscovered isotope of oxygen, along with a hydrogen nucleus, a proton, all right? Of course, oxygen was already discovered well before now, but not this isotope, all right? This is a new isotope of O, previously unknown. Okay, this is what got the ball rolling. 14 years later, Irene Curie and Frederick Joliot, this is the Curies, Marie and Pierre Curie's daughter, who followed in their footsteps. Remember, the Curies passed away. Marie due to radiation poisoning, and although her husband had it, remember I told you he died in an accident. But anyway, their daughter actually followed in her parents' footsteps and took over Marie Curie's lab when she had finished all her schooling. Anyway, 14 years later, they observed a similar transmutation from aluminum to phosphorus. Again, this is a new isotope of phosphorus, previously unknown. Now, notice that Rutherford used nitrogen, which is a fairly small atom, comparatively speaking, and Irene Curie used a larger isotope, one of aluminum. So in each case, they used an alpha particle to start this process. These particles can be used to bombard other nuclei with a particle accelerator, which makes them very fast, going very fast, to produce the nuclei of totally different elements. Using this process, beginning in 1940, scientists were able to artificially produce new elements on the periodic table by bombarding the nuclei of some of the heavier elements with small particles. So you see, Rutherford started small. The Curies went to even larger elements. So then the thought was, well, what's going to happen if we do it with a big element? All right. And this is exactly what happened. These new artificially produced elements, beginning with number 93, neptunium, that's the first one. For those of you that don't remember, uranium, number 92, is the last and largest naturally occurring element on the periodic table. Everything after 92 has been artificially produced via this process right here, including all the way up to 118. And the last few have just been recently discovered in the last several years. So these are called the trans-uranium elements. They're after uranium. So we took uranium-238, bombarded it with a neutron like we talked about earlier with a chain reaction, which nuclear fission, and it produced the unstable isotope uranium-239, which then immediately decayed or decomposed into neptunium-239. This is atomic number 93, which did not exist until now, and a beta particle. All right. So why did we do this? Why did we produce the transuranium elements? Well, think about it. So this is in the 40s and 50s. World War II is over. We've dropped nuclear bombs on Japan, brought an end to World War II. But now we're in what's called the Cold War, those of you that have studied this in history. So there's a buildup of nuclear weapons, both by the United States and by Russia. And so the thought process was, we're using uranium to do this. And so if we need to build up an arsenal of nuclear weapons, and again, at the same time, we started to decide, well, hey, why don't we use nuclear energy to produce electricity? Either way, uranium is a non-renewable resource that we dig out of the ground. At some point, it's gonna run out. And if we need nuclear energy, what are we going to do? Well, producing these artificially produced elements. The thought behind it was, well, now we can have an alternative source of nuclear fuel for our reactors and for our weapons. And so in reality, so this started in the 40s. World War II didn't end until 1945 when we dropped the bombs on Japan. And in fact, that second bomb that we dropped on Nagasaki was actually a plutonium bomb. Plutonium is atomic number 94. It was the second transuranium element produced artificially via this process. And so when we dropped that bomb on Nagasaki, and you can read this in the history books or online, we didn't know if it was going to work or not. All right, we knew that the uranium bomb worked, obviously, but we were testing this new artificially produced element, plutonium, to see if it actually worked. And of course, indeed it did. And so several of our nuclear reactors, even today, use plutonium as their fuel source. Many of them still use uranium. So over the course of years, as all these new elements are being produced artificially, the initial impetus behind that was, of course, using as nuclear fuel. But now more today, in the later stages of that, it's been more geared towards medical research. Of course, we use radioactive isotopes in what's called chemotherapy to fight cancer and other things. So now a lot of the shift in the thought process of artificially produced elements has been geared more towards medical reasons rather than energy reasons. Okay, so let's talk briefly about half-life, and we're going to head to the back. So a radioactive half-life is the time required for half of an original sample of a radioactive nucleus to decay. So here on the next page, raise this up a little bit more. If we start with 1 gram of a radioactive isotope, the time it takes for that gram to be cut in half to a half a gram is the amount of time that we call a half-life. All right? Let's say, for example, and a half-life we express as t to the 1/2. All right. Let's say, as an example, that the half-life time is equal to 1 year. All right. We'll just make it simple. 1 year. So the time it would take for a gram of this radioactive substance to decay to a half a gram is a half-life, and in this example, that time would be 1 year. All right. The time. So this is first half-life. When that half a gram decays to a quarter of a gram, it's been cut in half again. So now we've undergone a second half-life, which is another year, which is 2 years total. Okay? 2 years total. A third half-life will cut that quarter gram in half again, now down to 1/8 of a gram. And so now we have another year that has gone by, and now we're up to 3 years total. Do you see the pattern here? If we undergo a fourth half-life, which cuts that 1/8 of a gram down to a 1/16 of a gram, which would be, let's see, 0.0625, I believe. I think. Yep. Which would be 1/2 times 1/2 times 1/2 times 1/2, 4 times. All right. So now we add another year, and now we're looking at 4 years total. All right, 4 years total. That's in effect how it works. Okay. So now let's graph that. All right, let's graph it. This is what we're going to do in your lab today. So if we graph that, and we do our mass over here in grams, and we do the time down here in years, since our half-life is in years. All right, so let's start up here with 1 gram. So this would be a 1/2 gram, and then that would be a quarter, and that would be an 8.125, and half of that would be a 16.0625. So at time 0, right, we're starting with a gram. All right, after 1 year has passed, we're down to a 1/2 gram. After a second, just going by what we did up here, after a second year has passed, we're down to a 1/4 of a gram. After a third year has passed, we're down to 1/8 of a gram. And after a fourth year has passed, we're down to a 1/16. You see what we're graphing here? Look at this. You see what we're doing? What kind of relationship is this? It's a hyperbola. It's an inverse relationship. Right? As the amount of time increases, the mass remaining decreases. All right? Does it ever hit 0? No. That's one thing to remember in regards to radioactive decay. Is it ever going to decay to where we have 0 radioactive material left? No, it's not. But that's not the concern. The concern is, how long does it take to get down to a level where it's no longer harmful to biological life, such as ourselves, or plants, or animals, or whatever. Okay? So it's not that it goes to 0, because it's never going to. It's how long does it take to get it down to a level that is so low it doesn't matter whether it's around us or not, because it's not going to affect us. Okay? That's the key. All right. We're going to stop there. We'll pick up with that in our next lesson tomorrow. So let's head back. We're going to be doing exactly this back there in the lab. So let's head back there and do that now. Unplug here. Okay. Now I've got this set up a little differently because I want. Hopefully you can be able to see this as I do it. So I'm going to have to fiddle around here with the laptop just a second. I got it way up high. Let's see if I can turn it down. Oh yes, there we go. If I scoot that, no, not about right there. Of course, my head's cut off. Sorry. All right. I guess I'm the headless horseman. If you've ever watched that movie, came out quite a while ago. But anyway, never mind. Don't worry about looking at me. This is what's important right here. All right. So here is our lab paper today. All right. Don't forget to answer question 1. What is the definition of a half-life? I'll tell you what. I'll kneel down here until I'm ready to start working. Okay. Which we just talked about a little bit ago. So we're going to measure the rate of decay of pentium, which is a made-up name, pennies, and determine its half-life. All right. So we're going to start with 100, pennium atoms, 100. All right. We're going to sprinkle them randomly in the bottom of the box, like so. See the lines, the grids there. Any pennies that touch the lines are decayed, and out they go. All right. Remove those and set them aside. We won't use them again. Gather the remaining undecayed pennies, atoms, and sprinkle them again. And we're going to remove the ones that hit the lines, just like we did before. We're going to keep doing that however many times it takes until we get down to either 0 or 1 penny. All right? So I'm going to do that, and then we'll write it down. Okay? So up I go, and I become the headless horseman again. All right. So I'm going to sprinkle it in there. There we go. You see them? I'm going to pull out all the ones that are touching the lines. That one, even if it's barely touching, get rid of it. That's it. Out, 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 out. Okay. Out, out, out. Yeah. Give me a minute here. It won't take too awfully long. That one's out. Yep, yep, yep. Yep, yep. About got it now. No, that one's touching. So is that, so is that. Those two are, those. That one is, that one is, that one is. Let me see. Oh, there's another one. Think I got it. Yep. Okay. So, on your lab paper, we're starting, of course, at times 0. So at times 0, we had 100. All right, we had 100. And now we've just done 1 half-life. So next to the 1, we want to know how many pennies are left. All right. So these are the ones that were decayed. I'll put them in there. And, well, actually, I'll just set them aside because I'm going to use this cup again. So I set those aside, and I count the ones that are left. All right. So let's see. Looks like I got 63. 63. All right. That's it. So next to the, lost one. Next to the 1 under pennium atoms remaining, 63. So now I got 63. I'm going to do the same thing again. All right. And again, if they're touching a line, get rid of them. Okay. Yep. Definitely that one. That one. Okay. That one. That one's touching. Nope. Yep. 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 I think that's it. So these go out. What do I got left? Oh, that one's touching too. Never mind. So with that one. Okay, after the second throw, I'm down to 39 pennies. 39. So next to the 2, under trial 1, 39. So put those 39 back. Do it again. And now we're on trial 3. Okay, those out. Getting a lot easier now. There's a few of them in there. Doesn't take quite so long. Okay. Okay. Those are out. So I got one. A lot of them up here in the front corner for some reason. Okay, after that, 24. So trial number 3, we have 24 left. Uh-oh. Penny slid under the slot there. There we go. 24. Yep. 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 Definitely that one. For some reason, I keep getting them up near the front there. I'll try and get it better this time. Let's see. Okay, with all those over there. And I now have, after number 4, 17 left. Yeah, 17. All right. So 17. Now we're ready for trial 5, which is be the 5th half-life. Okay, we're going to run there again. Okay. Good. Not very many on the lines now. Not this time. That's it. All right, so 12. So after 5, we got 12. Okay. All right, got a few more now. Yep. 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 That's it. Okay, put those over there. And I got 6. All right, so after trial 6 or half-life 6, we have 6 left. Getting close now. Ready for 7? Okay, oh, only 2 on the line. Now I'm down to 4. The other one you couldn't see, it was up there in the corner. All right, so after 7 trials, we're down to 4 pennies. After 8, we are down to 2. All right, here we go. Here we go. Oh, and 1 hits the line barely. All right. So after half-life number 9, we are down to 1. I said end at 0 or 1. There you go. Okay, so we've completed the task for trial 1. Now, if you remember, we do 2 trials. If you look at the paper, you'll see that. But for time's sake, we're just going to do the 1. However, I did the second one before, and I do have data for that that you will record. Okay. In fact, I'll run through it here in just a second. When I get these pennies gathered up here. There we go. So to reiterate, let's set that aside. And I'll put that, actually we'll just put this back here. Now we can see much better. There we go. All right, so let's run down the first column again, okay? So at 0 times 0, we had 100. Then the first one, 63. Number 2, 39. Number 3, 24. Number 4, 17. Number 5, 12. Number 6, 6. Number 7, 4. Number 8, 2. And number 9, 1. So it took 9 half-lives, 9 throws, to get it down to 1. All right. Now I went ahead and did a second one earlier, and I'm going to give you those numbers right now. All right. So this is trial 2. Of course, at 0, we started at 100 again. Number 1, 59. 2, 38. 3, 23. 4, 15. 5, 10. 6, 6. 7, 4. 8, 1. And 9, 0. So again, I ended on 9 half-lives. That not necessarily doesn't happen every time, but that's okay. And so now we're going to go to the average. And if you'll see up here, I said round to the whole number. See that right there? Round to the whole number. So you just, for trial 1 and 2, add them up, divide by 2, and then round to the nearest whole number, because we're going to record by whole number. So, of course, the average for time 0 was 100 and 100, which is 100. The average between 63 and 59 for trial 1 was, of course, 61. 39 and 38 would be 38.5, which would round to 39. Number 3, 24 and 23 would be 23.5. That rounds to 24. 4 and 5 were, or I'm sorry, 4 was 17 and 15, which rounds to 16. Number 5 was 12 and 10, which rounds to 11. And then number 6 is 6 and 6, which averages to 6. 7 averages to 4. 8 is 2 and 1, which is 3 divided by 2 is 1.5. That rounds to 2. And the last one, number 9, is 1 and 0, which is averages 0.5, but that rounds to 1. So again, our averages are 100 for 0. 1 is 61, 2 is 39, 3 24, 4 16, 5 11, 6 6, 7 4, 8 2, and 9 1. If you missed those, I know I said them twice, but I said them kind of fast. Of course, you can always stop the video and rewind and go back. Now let's go to the back side. So here is the graph. All right. So here's what we're going to do. On the y-axis, this is mass. Actually, we didn't do mass. We did number of atoms or pennies. So we'll label that atoms. All right. Atoms remaining. And with the number of boxes I have there, I went up by tens. So let's go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, which gets us to where we need to go. And then the y-axis is time, or the x-axis, excuse me, is time remaining. All right. Now, as I said on the front, our make-believe half-life is in minutes. All right. So this time remaining would be in minutes. And again, I just went by ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And luckily, we finished at 9, so we're good. So we start, of course, at time 0, and we had 100, so there would be a data point there. And then at time number 1, we had, what was our average at time 1? 61. So it would be just a little bit over 60. At time 2, our average was 39. So here at the 2, we would go up close to 40 there, put our point there. And then you continue to do the same. And again, it's an inverse relationship. So as you graph this, and you do this at home, as you graph it, you're going to get a very nice hyperbola, all right? Just like you're supposed to. Now, how do you determine the half-life time? Because if you go back to the front, it asks you, record the half-life of pennium here, including units. All right, so how do you do that? Well, we started with 100 pennies. The amount of time, a half-life is the amount of time it takes for that to be cut in half. All right, so if we started with 100, where is it cut in half? Well, when you get to 50. So here's 50 on the graph, right here, 50. So I go across until I hit our curve, our hyperbola, and I marked it there with a little X, and then we run it down to the X-axis, and lo and behold, for this particular data, that X is almost right smack dab halfway in between 1 and 2. All right? So I, again, subjectively, of course, reading a graph is always subjective, I recorded it as 1.5. And so on the front here, our half-life time would be 1.5 minutes. Okay? So what you are then to do is look at problems 12 and 13, which we discussed up on the board in class. And you are to interpret this graph, just like we did this one, and the one we did up on the board earlier, and answer the questions based on this interpretation of your graph. And then question 13 has to deal with neutron-induced fission, all right, which is a nuclear transmutation. It's a type, that is. It's a chain reaction, remember, we talked about that. It gives you some information here, and you are to go ahead and complete that. It'll be very, very similar to what we did up on the board earlier, okay? So this is due tomorrow, all right? You're going to turn it in in class when you return to school tomorrow. Again, I'll have the key posted by 7 a.m. tomorrow morning so that you can check it at that time. Okay? Or you can check it here at school or at home. Okay? So I think that's it for today. So hope you enjoy your e-learning day. And I will see you all tomorrow here in class. So hopefully anyway. So until then, this is Mr. Keister signing off. Everybody take care. Stay safe. Keep working hard. And I'll see you tomorrow. So long, guys.